if we speak about chemistry, it took a deep role in human society. For a couple of last centuries, the role of chemistry, the impact of chemistry on human society grows higher and higher. And if we speak about the impact on food industry would be a first vivid example. So if we put aside the dichotomy of correlation and causation, the correlation here is striking. So the human population growth in the 20th century was really high, and it grew along with the growth of fertilizer production. And we can consider fertilizers as quite simple compounds, but fertilizer production relies on, first, materials chemistry. Fertilizer production rests on two chemistry fields. First of all, it's materials chemistry. It's production of steel, electrics, and reactors, chemical reactors. And next, it's catalysis. Just remember the story of Fritz Haber, who invented the process of production of NH3. Next, we should consider the impact of chemistry on the healthcare industry. The life expectancy in the developed countries rose in the recent decades significantly, and it's projected to grow in the next decades. So what are the sources of that? It's development of materials chemistry for medtech, development of medicinal chemistry, drug design. And speaking about organic chemistry, it's a foundation of these two. So what would be approach to gain a new insight, to gain a new knowledge, to gain new compounds with target properties? We have heuristic guess, like dig here, based on our theories, models, etc. Next, we conduct research. We conduct experiments, and these experiments may be productive or may be unproductive. And via conducting research, we expect to have new substances with target properties, with desired properties. Should it work? Well, could you comment on that? Should it work always? Or even does it work?
You can't predict every property always. So.
Yes. Moreover, most of experiments are unproductive. So most experiments fail. First of all, result is not guaranteed. Next, optimal properties are not guaranteed. Classic research is really expensive, and it's time consuming as well. Later, in the recent decades, we also consider the potential harm for environment. So what would be the problems in classic approach to research? Here I want to make a reference to a lecture by Yuri Allen. So he says in his TED talk, then we have a theory, a model. Next, we expect some result. Should it be a compound, a material, whatever? or maybe even new scientific knowledge. However, we get in a situation when experiments don't work, experiments don't work, experiments don't work. And such a situation may take quite a lot of time. He calls that a situation a cloud. So every seasoned researcher was in such a situation when you don't know where to go in your research, what approach to take, what new model to apply. And being in this cloud quite often gives us new unexpected knowledge, unexpected substances or materials. How it's so? We, for example, writing a grant proposal, we expect some results. However, we don't know all the underlying, let's say, nature, laws of nature. And we get unexpected knowledge. Is it better? I think yes, because it's really true knowledge. And we can speak of serendipity. What is serendipity? It's a fortuitous discovery of something that was made by chance, completely by chance. If we speak about penicillin, it's a serendipitous discovery by Alexander Fleming. That was, well, how the discovery was made. It was an impurity in laboratory glassware, impurity by mold. And this mold was shown, exhibited antibacterial properties. Alexander Fleming tried to persuade the research community to believe him that it's an important fact, but they didn't believe him for decades. After all, he was successful in his discovery. But anyway, it's a serendipitous discovery. Next, we can speak about Belousov-Zhabotinsky reaction. For someone new to physical organic chemistry, it's a kind of reaction that was expected to be completely forbidden by thermodynamics. It's an oscillatory process where reaction vessel change, where the solution changes its color in an oscillatory manner. And serendipity may come or may not. So how can we accelerate such a process? Here, rational design with machine learning comes. So we want to get new substances, new materials with optimal properties. We have two things. First of all, we have scientific data. It's data from previous research, databases, research articles, lab notebooks. By the way, don't underestimate this stuff. Lab notebooks are very, very precious in machine learning studies. Next, we have machine learning algorithms. And what we want to do? We want to combine this and build our machine learning models using the data at hand. Why? To have a research with minimal associated cost, to save time, to save money, and also to save environment by reducing possibly toxic waste. So how can we implement such a paradigm in research? We can perform computational screening, virtual screening of compounds. Let's say we have a huge library of potentially active compounds, let's say millions, and we apply consecutively machine learning models one by one. So we filter out compounds that are potentially inactive, and we have a small number of hits that should be productive, that should be good. So we predict in such a way new compounds with optimal properties. Okay, so that would be a paradigm of virtual screening. But can we accelerate serendipity? Yes, we can. And that was proposed by David McMillan several years ago. He proposed that for organic methodologies. What they did? What did they do? So they had a substrate pool. For simplicity, it's a huge number of organic substances that are combined in various ways. The reaction, we conduct many reactions in parallel. We combine with many combinations and with under different conditions, under different reaction conditions. We apply catalyst. We introduce catalyst in the system. And after performing the reactions in parallel, we analyze post-reaction solutions. Some of them are reactive. This gives us information on potentially new reactions. And a chemist analyzes the data. Is it potentially so? Can we find some new data, new reactivity in this pool? If yes, optimize such a reaction. What does this mean? This means that taking one reaction from a pool, we optimize catalyst and conditions for this particular combination of substrates. And in fact, it was productive for organic chemistry. So the laboratory of David McMillan proposed such a paradigm, and it was successfully applied in organic chemistry for several reactions. The foundation of accelerated serendipity is high throughput experimentation. What's that? Are there people for whom organic chemistry is complex and who's new to organic chemistry? Well, here I give a reaction equation for an organic reaction that is catalyzed by a palladium catalyst that can be combined with different phosphine ligands. So it's compounds of phosphorus that react with palladium metal complex. They are combined with different bases, with different solvents, and under different conditions. So we take such a platelet. In this platelet, every hole is a small reactor that can be pressurized, that can be heated, and we can conduct a reaction under high pressure. So such a paradigm is called high throughput experimentation because we, by using this, we can conduct many experiments in one day. So we combine different reaction conditions and find optimal. For example, here, some combinations give us higher yields than others. But can we combine accelerated serendipity and rational design? And why should we do that even? Do you have any idea on why?
Why should we do rational design?
Why should we combine rational design and accelerated serendipity? So what's the problem with rational design? What's the problem with virtual screening, like this one?
You should have data for prediction.
Yes.
Models.
And also, we base on the known data. And I would say that such an approach of rational design of virtual screening gives us information that is derivative from the data we have. So it's a new data in some sense, but also it is not. So you can infer that something can be active. To gain a really new insight, we have to have some serendipity. To combine that, we need to take a different approach. What's that? It's a so-called computer. In fact, it's a robot. Here we have some laboratory glassware that is used to mix reagents. We, for example, have a rotary evaporator to isolate new compounds. Under the bench, under the laboratory bench, there may be mass spectrometers, there may be analytic labware to analyze reactive solutions. And here we have pumps. These pumps control the reactions. They pump in and pump out needed solutions. And these pumps are programmed by a computer that operates a machine learning algorithm that is self-correcting. So how does it go? For example, we have a target molecule we need to synthesize. And we want to optimize reactions to synthesize it. We analyze possible reaction sequences to get it. Then we use special programming language that we will briefly discuss on the lectures. So we input a synthesis script that drives these pumps. Next, a robot performs a number of reactions. We analyze the data obtained and use it as an input for a machine learning algorithm. And the cycle goes on and on and on after it reaches some optimal synthetic path. So it's called a computer. Such an approach was proposed by Lee Cronin in his lab is based in Scotland, as I remember, in the Edinburgh University. There are alternative approaches to robotic chemical research, and we will discuss them as well. So the chemical robot is based on the feedback loop that allows us to search for new reactions, for new reactivity in an automated manner. And here I would also discuss what is artificial intelligence. As for me, I prefer to use a classic definition of that that is used among computer scientists for decades. So we can define a basic AI, like a program of in the elevator. It doesn't learn, so it reacts on existing conditions. And next we can have a limited AI. What that would be? So such a algorithm, let's say, makes decisions using available data. In chemistry, that would be a machine learning model that proposes new materials or substances with optimal properties. And in fact, most machine learning models in chemistry are limited AI. But to have really new data, to propose really new data for an AI, that would take such an AI would be an advanced AI. Here I stress non-derivative new ideas. What this is. So it's exactly that. And we can have such a Venn diagram. Yeah.
Face recognition is against not limited AI.
So you would propose to facial recognition that's you know, I agree with you. However, here I cite a book on machine learning. And for me, facial recognition uses available data. But is this a human ability? Should we define it as initially human ability or maybe ability of a living being, of an animal?
I guess that rats can recognize human faces maybe even better than modern algorithms in face recognition. I guess that rats doesn't have something like advanced AI.
Well, I agree that simple neural networks and first neural networks can be assigned to the limited AI class. But I think that from some degree of sophistication, that would be an advanced AI. So yes, you are right that it's a tricky question, should we assign it to one or another class? But for chemical machine learning models, they are for sure limited AI. And to be here, we need to have some robotic platform. Well, this is some kind of science fiction, but here we have a Venn diagram that gives us a classic view on what is artificial intelligence. Here, I should note, you should notice that machine learning and deep learning are different fields as proposed by the author. Why so? Do you know?
No, I don't.
Well,
Anyone?
We have classical machine learning. That means that the algorithms used are non-linear, but they are quite deterministic. And when we use deep learning, we use neural networks. They are both non-linear and non-deterministic in the ways that they are trained. So I believe that's the classical approach to dividing models. Classical machine learning uses math-backed algorithms mostly, and deep learning mostly uses neural networks in any way, shape, or form.
Well, yes, deep learning is concerned with deep neural networks. But what's the difference? What can we say also? What can we say more? Well, the difference would be in classic machine learning, we often need to perform feature engineering, and we will speak a lot about feature engineering in our course. We have to select variables, combine them, or probably make some mathematical operations on them to get descriptors or engineered features that are good predictors of target property. And with deep learning, the strategy is so that we have raw data, or it's as raw as we can get. That raw data is processed by a neural network with many hidden layers, and we usually avoid feature engineering. Of course, here a dichotomy arises, because we can have a very simple machine learning model that works really well due to feature engineering. And often in such a case, we need to train a deep neural network that is much more complex, that, let's say, performs feature engineering due to its topology. So many researchers divide these two disciplines. And also, what should I say? We should also notice that artificial intelligence encompasses both disciplines. Some researchers would say that artificial intelligence only rests here. But classic definition would be that artificial intelligence is a field of computer science that encompasses machine learning and deep learning together. So, what will we discuss in the course? We will begin by discussing common libraries used for machine learning, like scikit-learn. We will discuss data analysis in pandas. We will discuss data visualization in Plotly. I prefer Plotly to Matplotlib after some trial and error. It's much more convenient for me, and I hope to to demonstrate you that Plotly is much more powerful. It's a much more powerful library. Next, we'll discuss machine learning applications in various fields of chemistry. So we will begin by linear free energy relationships. What are these? Linear free energy relationships correlate some parameter with reaction constants. It could be a reaction equilibrium constant or reaction kinetic constant. And linear free energy relationships may be seen as some simple proto-machine learning models in chemistry. They were first. First linear free energy relationships were established in the 1950s. And in fact, they are used now as well. Why so? We will discuss that. But really impressive research is done with simple linear models like this. So we will discuss their place in modern organic chemistry. Next, we will discuss medicinal chemistry and how machine learning can be applied there. Why should we use machine learning in the medicinal chemistry? The reason is simple. It's this funnel. In a drug development cycle, we can have one approved drug. But what's the base of this funnel? Do you know how many drug candidates may be after the basic research? So what's the base?
Hundreds of thousands.
It's like in billions, maybe.
Tens of thousands, sometimes tens of thousands, or it can be hundreds as well. So such a cycle takes sometimes 10 years, and it can take up to 2 billion euros or dollars, or about that. So every pharma company would like to facilitate such a drug development cycle to make it less costly. And by reducing the number of potential drug candidates, they strive to do that. And in fact, medicinal chemistry was the first field of chemistry that adopted machine learning strategies. Medicinal chemists use machine learning for decades, in fact, and many good practices of medicinal chemistry, applying machine learning in medicinal chemistry, were transferred to other fields. So in drug design, we can have two paradigms. First, structure-based design, and also ligand-based design. So we can have a structure of a target for which we seek a molecule that fits it. So we will speak about, we will discuss the lock and key model and how it relates to drug development. But mostly we'll focus on ligand-based drug design. And in particular, we will speak about QSARs and QSPRs. What's that? It's quantitative structure-activity relationships and quantitative structure-property relationships. So in such a paradigm, we relate a structure of a molecule with a target property. It can be some metric of biologic activity. It's done via computing descriptors of molecular structure that encode it. And then we input molecular descriptors into a machine learning model, train it, and get a model of biologic activity. We will also discuss material science and how can we apply machine learning to discover new materials with optimal properties. But for now, I would like to make a pause. So, ребят, как вам, комфортно ли по подаче? Нужно ли быстрее? Что?
Is it all right?
Maybe more loud because that segment I can hear the sound of phrases from your speech.
Окей. Хорошо. So, in material science, the main aim for rational design is the same. We would like to get a material with optimal properties by using a machine learning model. It's a fruitful field in the recent years for a simple reason. Now there is an exponential growth of research papers on machine learning and material science that rests on the availability of data on materials. We will discuss some open databases of material properties. You can download data from that, from these bases, and you can use them. So again, the first step would be to formulate, to compute descriptors of material that encode its structure and relate material properties with its structure. Here I would also like to stress that mostly we will discuss supervised machine learning in chemistry. There are some tasks for unsupervised machine learning in chemistry, but well, it's not a rational design and it's not a classic topic. So we will discuss some basic topics that we can implement in Jupyter notebooks on practical sessions. We will also discuss the application of machine learning in catalysis. First, I will tell you about what a catalytic activity is. If we have a number of reagents and products that are produced via reaction from these reagents, we have several metrics of catalytic activity, among which the best is turnover frequency. So it's the frequency of turnovers via a catalytic cycle that is defined or known. And we, in our machine learning study, in our machine learning endeavor, want to find new catalysts that maximize turnover frequency. So, what can we do? We can vary catalyst structure. We can use different ligands. And for some of you, such a diagram, such a figure can be complex. Don't worry, we won't focus on the molecular structure. We will focus on what catalytic activity is and how to implement machine learning models predicting that. Of course, we will discuss how to encode molecular structure. And yes, we will do that. Among optimizations that can be done with machine learning models via virtual screening is the optimization of catalyst price. Why so? Many catalysts are really expensive substances, and if we consider homogeneous catalysts, they are really, really expensive. Sometimes catalysts can be more expensive than gold, for example, than platinum. And in fact, it can consist of platinum compounds or palladium compounds combined with ligands, synthesis of which is also very, very expensive. We will also discuss heterogeneous catalysis. Look at this diagram. So here we have a reaction network in which we input gaseous carbon monoxide, gaseous hydrogen, and even in such a simple system, we can have tens of intermediates and more than 2,000 pathways. The author of this publication used machine learning algorithms that we will discuss to decipher this network that cannot be modeled with classical quantum chemical methods. So in fact, chemists now can simulate chemical reactions by using software, but such a process would take quite a lot of time for this network. And you should also notice that the catalyst used is really simple. It's a simple metallic rhodium. So combination of carbon monoxide, hydrogen, and rhodium in a reactor can give a very simple, a very complex reaction network. Next, we will discuss organic synthesis and how machine learning and even deep learning can be applied to organic synthesis. What would be tasks for machine learning and deep learning in organic synthesis? What would you propose to be a good task, a proper task for machine learning or deep learning?
Building of photosynthetic trees.
Discovery of new reaction.
Maybe even more. What can you say also?
So optimize conditions for reaction.
Yes. So the first task would be to predict products of a given reaction. We combine two reagents. By the way, do you know what's that? Yes, it's an ion, so it's alkoxide. It's deprotonized. So it reacts in an organic reaction and gives a product. Authors of this paper proposed a deep learning model that correlates reagents with products. How the model does that? First of all, we have structures of reactants and reagents as SMILE strings. We will discuss what SMILE string is. And it processes it and relates to the SMILE string of the product. And here, I simplify the situation a little bit because the real situation is quite more complex. Because this paper, a natural language processing approach is taken to relate this, let's say, text to this text. So structures of reagents and products are related by using NLP, can be correlated by using NLP approaches. And next, we also can predict optimal reaction conditions. Why should we do that even? If we have an organic reaction, reaction conditions are critical to the yield and to reaction rate. By taking here, we have none. So we predict what's here. And here we can have solvent, catalyst, temperature, pressure, some additives, for example, salt additive. We can have all this. And a machine learning model should predict the conditions for a given reaction. Several labs were successful in proposing such models, and we will discuss one work, and we also it's also an online service, so we can access a site in which we input structures of reactants, products, and we can have a proposed optimal conditions via internet. So let's discuss the course structure. We will have
I was wondering about two things. First of all, it's about rational design. Can't we lose any potentially helpful reactions while giving our while preferring the rational design? As you noticed, there is a serendipity and
yes. That's a very deep concern for a reason, which is if we have some scientific data, we base our predictions on this data. And if we search for decades in one direction, for example, we know that some substances are active in a reaction, but we don't know that another class of substances is active. Or we don't know, for example, which new ceramics can be superconductive under some conditions. So we search only in areas we know previously. And such a problem also, I would say that, I should mention that such a problem is called the lantern problem. So if we, it's a story, anecdote of a man that is searching for something at night. A passing by person asks, what are you searching? So the man answers, so I'm searching for, let's say, something. But so where did you lose that? And the man replies, well, I've lost my item there, but you are searching like here under the lantern, under the lamp. Well, but here I can see what I'm searching for. So.
And the second question is connected also to serendipity. Is there a way to measure serendipity?
Do you mean that some discoveries may be more serendipitous than the others? What do you mean exactly?
You mentioned two discoveries, and those discoveries were made by your serendipity, by this principle. And I was asking if there is a way to measure this, this phenomenon.
Well, if you don't search for something and you find something purely by chance.
Is there a way to increase this chance?
By high throughput experimentation. So you can combine many reactions, many reagents under various conditions and perform reactions. So, and I only know the approaches I've told you about. Yeah.